S1, S2, S3, Sp are sums of infinite geometric series whose first terms are 1, 2, 3 and so on, and whose common ratios are 1 by 2, 1 by 3, 1 by 4, and for the pth term it is 1 by p plus 1 respectively. Prove that S1 plus S2 plus S3 plus Sp is equal to p by 2 p plus 3. Now this looks like a very lengthy problem, but surprisingly it is a very easy problem to solve. Let us see what S1 is. Okay, so first let us write what is S1 going to be. S1 is going to be the infinite geometric series, that is, it is the sum of the infinite geometric series whose first term is 1 by 2. Sorry, whose first term is 1, right? Whose first term is 1 and common ratio is 1 by 2. So S1 is going to be, what is the formula for the infinite geometric progression? It is 1 divided by 1 minus r. So it will be 1 divided by 1 minus half, and this will be equal to 2. Similarly, what is S2 going to be? S2 is 2 divided by 1 minus 1 by 3, which is equal to 2 divided by 2 by 3 is equal to 3, and S3 is going to be 3 divided by 1 minus 1 by 4 is equal to 3 divided by 3 by 4 is equal to 4. So you can already see that this is a very simple arithmetic progression that we are getting. What is Sp going to be? Sp is simply p divided by 1 minus 1 divided by p plus 1, because it is this sum of infinite geometric progression with the first term as p and the common ratio as 1 by p plus 1. So what you get is p divided by p plus 1, and this will be equal to p plus 1. So what is our S1 plus S2 plus S3 plus Sp? Let us call this sum as let us say T. So what is our T equal to? T is simply S1, which is 2 plus 3 plus 4 up to Sp, which is p plus 1. So this is a simple arithmetic progression, and I can use the formula of n by 2 first term plus last term, right? What is n here? How many terms you can see here? You can see that there are p number of terms, right? Why? Because you can see if it is 2, at n is equal to 1 it is 2, at n is equal to 2 it is 3, so at n is equal to p it is p plus 1. So there are p number of terms divided by 2. What is the first term? It's 2. What is the last term? It is p plus 1, and we are done. So your sum is p by 2 times p plus 3, and this problem is done. Now let us look at problem number 23. Problem number 23 is that if r is less than 1 and is positive, okay, so we know that r is positive and it is less than 1, and m is a positive integer, show that 2m plus 1 times r to the power m times 1 minus r is less than 1 minus r to the power 2m plus 1. Now this is a slightly tricky problem and it uses some skill. So let me write this inequality in a slightly different way. I can write this inequality as 2m plus 1 r to the power m is less than 1 minus r to the power 2m plus 1 divided by 1 minus r. This inequality is same. Remember that 1 minus r is a positive quantity, okay? So you have to remember this r mod, sorry, 1 minus r is always greater than 0. Why? Because r is less than 0 but is a positive quantity. So that is why we can simply divide both equation by 1 minus r, and this inequality will hold, right? Now what do you think is the right hand side? What do you think is the right hand side? Right hand side is the geometric progression. It is the sum of the geometric progression where the first term is 1, common ratio is r, and there are 2m plus 1 terms. So let us consider this series in more detail. We have to prove this, right? In order to prove this, we have to prove this. What we can see from this right hand side expression is that this is actually sum of a geometric series. Let us call it S. It is the sum of geometric series 1 plus r plus r square, and how many terms it has? It has 2m plus 1 terms. So what it means is it is sum of this series, right? You can see that if I add 1 r square up to r to the power 2m, I have 2m plus 1 terms, and if I want to find the sum of this series, it is given by this expression 1 minus r to the power 2m plus 1 minus r, right? So far is clear. So let us write some more terms here, okay? There is a reason that I am writing it. So I know that the last term is r to the power 2m. The term before it would be r to the power 2m minus 1, and r to the power 2m minus 2. This is the term that we are adding, and this is the right hand expression. S is actually equal to this, right? Now consider the first term and the last term, right? If you consider the first term and the last term, you will see that 1 plus r to the power 2m. What can I do to complete this as a square? I can subtract minus 2r to the power m plus r to the power 2m, right? Now if you look at this expression can be written as this expression can be written as 1 minus r to the power m square, right? And we know that anything which is square is always greater than 0. So from this expression what we know is that this expression is also greater than 0. So if this expression is greater than 0, this expression is greater than 0, we know that 1 plus r to the power 2m is also greater than 2 times r to the power m, right? All I have done is I have this expression 1 plus r to the power 2m. Now I am considering this expression 1 minus 2 r to the power m plus r to the power 2m. I know that this I can write it as 1 minus r to the power m square. This being a square is always going to be greater than 0. So we know that this expression is always going to be greater than 0. And if this expression is greater than 0, we know that 1 plus r to the power 2m is greater than 2 times r to the power m. Now, as another example, let us consider r, that is the second term and the second last term. So this one I can write as r plus r to the power 2m minus 1. Again, if I consider this expression like this, r times 1 minus r to the power 2m minus 2, this expression is same. Now again, this expression I can complete in form of square, right? I can write this as 1, sorry, this is plus over here, so I can write this as 1 minus 2 r to the power m minus 1 plus r to the power m minus 1 square. If I consider this expression, this means that this will be actually equal to 1 minus r to the power m minus 1 square, and this expression is also going to be greater than 0. So let us consider what happens if I have r times 1 minus r to the power m minus 1 square. You will see that this is equal to r minus 2r to the power m minus 1 times r, which is minus 2 times r to the power m plus r to the power m minus 1 square, which is 2m minus 2 times r. So 2m minus 2 plus 1 is 2m minus 1. This should be greater than 0, and from here you get that r plus r to the power 2m minus 1 should be greater than 2 to the power 2 times r to the power m, right? So this expression is also greater than 2 to the power 2 times r to the power m. Now similarly, you can consider any two expressions. Okay, you can consider r square plus r to the power 2m minus 2, and you will be able to prove that this expression is also greater than r to the power 2m minus is greater than 2 times r to the power m. So in general, let me show it that this is going to be true for all the expressions. So I will say that, let me say that we are trying to prove r to the power k plus r to the power 2m minus k. All I have to show is that no matter what the value of k is, it is always going to be greater than 2 times r to the power m. So for this, all I have to do is I have to consider r to the power k times 1 minus r to the power m minus k square. If I consider this, r to the power k times 1 minus 2 times r to the power m minus k plus r to the power 2m minus 2k. Now this expression is always greater than 0 because r to the power k is 0, this is a square, is always greater than 0, is always greater than 0. So this means that r to the power k minus 2 times r to the power m minus k plus k is 2 r to the power m plus r square 2m minus k minus 2k plus k is equal to 2m minus k is greater than 0, and we are done. R to the power k plus r to the power 2m minus k is also greater than 2 times r to the power m, right? So far what we have seen is how many terms are there? There are odd number of terms, right? There are odd number of terms here from 1 to 2m plus 1. Okay, what is the middle term going to be? Middle term is going to be r to the power m over here. So except r to the power m, you will be able to pair up all the other terms in the series. So for example, you can pair up 1 and r to the power 2m. You can pair up r to the power 2m minus 1. You can pair up r square and r to the power 2m minus 2. So all will be paired up except r to the power m. So if you add all these pairs, we know that this pair is greater than 2 times r to the power m. This pair is also greater than r times 2 to the power m. So how many pairs are there? There are m pairs like this, right? So we know that 1 plus r to the power 2m is one pair, plus r plus r times 2m minus 1 is the second pair, plus r square plus r to the power 2m minus 2 is the third pair, and so on. There will be m number of pairs like this, right? There will be m pairs like this, and in the end you will be left with r to the power m, because this r to the power m cannot be paired up. Now this should be greater than, this is greater than this is greater than 2 times r to the power m. This is also greater than 2 times r to the power m. This is also greater than 2 to the power r times 2 to the power r, sorry, 2 times r to the power m. So we know that this is greater than m times 2 r to the power m plus, this is rm over here, so I'll just copy rm like this. Now if you take out r to the power m as the common factor, you get 2m plus 1 r to the power m. And what did we want to prove? We wanted to prove that 2m plus 1 r to the power m is actually less than this sum, and we have proven it. This sum is actually greater than 2m plus 1 r to the power m. So this is done, right? So we know that this relationship is true. We have already proven that 2m plus 1 r to the power m is less than 1 minus r to the power 2m plus 1 divided by 1 minus r, and therefore we can prove whatever the statement of the problem was. We can say that 2m plus 1 r to the power m times 1 minus r is going to be less than equal to 1 minus r to the power 2m plus 1. So this is the first part of the question. The second part of the question that they want you to prove is, they are saying that hence show that n r to the power n is indefinitely small when n is indefinitely great or n is indefinitely large. So how to proceed further? What I can do is, I can, instead of putting m over here, let me change it by n, right? So let me say that let n is equal to 2m plus 1. This means that m is going to be equal to n minus 1 divided by 2. Now simply put the value of n over here. So this expression means that n times r to the power m is n minus 1 by 2, n minus 1 by 2 is less than 1 minus r to the power n divided by 1 minus r, right? And now this means that n times r to the power, I have to get r to the power n over here, so let me say that this is r to the power n. How can I make this r to the power n? All I have to do is take the square of it and then multiply it with by r. So, or what you can do is, this is equal to 1 minus r to the power n times 1 minus r. How should I get n over here? N minus 1 by 2. This is how what I should multiply on the right hand side. This is actually equal to 2n minus n plus 1 by 2 is equal to n plus 1 by 2. So if I multiply by r to the power n plus 1 by 2 on the right hand side and the left hand side, I will get n to the power n times r to the power n, and over here I will get r to the power n plus 1 by 2. Now what do you think is this expression? This expression is always going to be greater than 1. Why? Because this is the sum of the geometric progression starting with 1 and the common ratio is less than 1. So no matter how large n is, even if n is infinite, this is always going to be slightly greater than 1. If it is slightly greater than 1, it means that n to the power n is actually less than r to the power n plus 1 divided by 2. And now you can see, if I make my n very large, r being less than 1, my r will be very small, and therefore n r to the power n will also be very small. And this is what they are asking you to prove in this question. They are asking that if I make n tends towards infinity, what is n tending towards? If n tend towards infinity, I know that r to the power n plus 1 by 2, r to the power n plus 1 by 2, let me write it like this, r to the power n plus 1 by 2 will tend towards 0, and because nr to the power n is even less than this, nr to the power n will also tend towards 0 as n tend towards infinity. And we are done.